All right, last time we talked about Lavier theories, and I ended up mentioning that there is a connection between Lavier theories and monads, but not all monads. So monads are sort of more general than Lavier theories, and the kind of monads that actually correspond to Lavier theories, at least in the basic formulation of the theory, are the ones that are called finitary. And finitary means that the action of a functor on any object can be expressed as by its action on, or in a set as its action on the powers of a set. So like for all finite powers of a set. So it sort of looks like you can write it down as power series. So it's a functor that can be expanded as a power series and on powers of an object, right? Which kind of makes sense because in Lavier theories we were dealing with this tower of power, right? So these were all powers of one object. So it's natural to think that they will describe things in which everything is actually determined by how the functor acts on these powers. So in order to explain what a finitary container is, finitary functor actually is something that very closely corresponds to the idea of a container. Right? Remember functors as containers. Some of them are more like containers, others are not really, like the continuation monad, for instance, is not, very much not like a container, and in fact it's not a finitary monad. So these finitary functors corresponds to what normally people would call containers. Okay, so now we know which ones are containers, but we don't know what finitary means. So in order to define finitary functors, we have to define what ends are and coends. Okay, actually coends define. So ends and coends correspond, they generalize the idea of limits, and in particular products. So in a sense, an end is like an infinite product. I mean, you can have finite products, like, let me start by reminding you how we define a product. So if you have a product of two objects, A and B, right? We create things that are called cones. Okay. In this case, this is the simplest cone when you pick an apex. So an apex is always some particular object, and this sides of the cone are morphisms that go to the base of the cone, right? In this case, the base is just two objects. So we fix two objects, then we have these two things that we call projections P and Q. Okay? And the product was the best such object. Because there are lots of objects, in particular in set, there are lots of objects that have, most of them have morphisms going to any particular pair of objects. So this is not a big deal. But these cones, they form a category of cones. Cones are objects in this category, and we have to define morphisms. So a morphism between two cones, like once we fix A and B, right, then another cone, let's call it like C prime, right, differs from this cone only by having a different apex and different projections. So let's say P prime, Q prime, right? So if we have two cones like these, what would be a morphism between these two cones? It would be a morphism between apexes. So this is a morphism H, right? But these morphisms, they have to preserve the coneness of these diagrams, right? So they have to commute with the projections, right? Which means, like, if you take a projection from C prime to B, with Q prime, it should give you the same as if you first did the morphism and then the other projection, right? So you want this diagram, this triangle to commute, and you want this diagram to commute, right? So the commutation of these diagrams means that this morphism H, if it exists, it preserves the projections, right? So it's a good morphism between these cones. So this defines a category of cones, right? We have objects and we have morphisms, and you can check that there is an identity morphism between cones. That's just an identity morphism H, right? And then they obviously are associative. And the combination of morphisms is again a morphism, right? So they compose nicely. So it's a very nice category. And if in this category of cones you have a terminal object, then this terminal object would be called the product. Not in every category do you have a product, but if you do, it's a terminal object in the category of these particular cones. Okay, and then you can generalize this picture, right? And you can say, well, I can have maybe something. I can define a product of. Well, I use that letters, so let's say D, right? I can define a product of 3 elements, right? And then I would have these cones that are sort of wider cones, right? They have 3 projections instead of 2 projections, right? That would be a triple. We would call it, in set, it would be like a Cartesian triple, right? And in general, you can have tuples defined this way. So you can extend this stuff to a product of a finite number of elements. Then you can generalize this stuff by saying, oh, what if I have also morphisms that go in the base of the cone, right? So it's a different color maybe. Like if I have some morphisms here, then I will define my cones so that they also preserve these morphisms, right? So a cone, like if I have a cone here, I would want this path, right, to be the same as this path. So within a cone, I want these faces of the cone also to commuting triangles, right? And that way, I would define a limit. So a limit is a generalization of a product or a cone in which you have these morphisms in the base. And there is a way of doing this by saying, actually, what does it mean to pick objects and morphisms? Well, it means defining a functor from some really simple category. In this case, you have a category which only has 2 objects, A and B, and no morphisms other than identity morphisms, right? Then you can say a functor D from this category to my category C, it just picks 2 objects, A and B. Well, okay, these are, let's call them 1 and 2, okay? And 1 is mapped to A, 2 is mapped to B, right? I can pick a more complex category. I can have a category with morphisms in it. Then the functor will also pick a morphism here, right? And so on. I can make it as complicated as I want. And now a limit would be, well, I have to pick, or a cone, I would have to pick an object C. What does it mean to pick an object C? It means also that I have another functor. I can do this using a functor that's constant functor. A constant functor maps every object into one object in C, let's call it C, right? And maps every morphism into the identity morphism. So now that I have two functors, delta C, that's the constant functor, and D, I can say, I can define a natural transformation between them, and the natural transformation between them would be a family of morphisms, and this family of morphisms forms the sides of my triangles, the sides of my cone, right? And why do they have to commute? Well, they have to commute because of naturality condition. So the naturality condition for this natural transformation means that these triangles have to commute. These are sort of like a naturality squares, but with the top shrunk to a point. So they become naturality triangles. Okay? So this is like a recapitulation of the old stuff that we know from previous lectures, right? So this is how you define these limits, and in particular products. Now we want to generalize this to slightly different type of functor. So we're going to generalize this functor D to something called a profunctor. Okay? Profunctor. And in general, a profunctor is just a functor, but it's from a very specific kind of category. So in most general case, this would be a functor from a product category. C of D to set. So that's a kind of general definition of a profunctor. It is a functor, right? But the source is a very particular category, which is obtained by taking a product of two categories. So an element of this category is a pair of C and D, an object from C and an object from D. So that's an element of this product category. And a morphism is a pair of morphisms. So it's a pair of morphism F and G, but F goes sort of in the opposite direction. So it goes from C prime to C, whereas G goes from D to D prime. Okay? Because this is opposite category. So in a picture it would be, you have C and D. Well, okay, so you have a pair CD, right? And you have a pair C prime D prime. A morphism from CD to C prime D prime is a pair of morphisms, one going from C prime to C and one going from D to D prime. And you might be thinking, why are we doing this? Why is this one going in the opposite direction? Well, it turns out that there is a very nice example of a profunctor that we use all the time, and that's the home functor. The home functor in category C, from A to B, right, is a profunctor in A and B. So it's a mapping that takes a pair of objects, A and B, to a set of morphisms from A to B. So that's one part of the definition of a profunctor. It takes a pair of objects, right? What does it do to morphisms now? So it takes two morphisms, a pair of morphisms like these, right? And it has to lift it to map CAB to CA prime B prime, right? So if we have, so maybe I should change these labels here. So this is AB, this is A prime, B prime, right? So if F goes from A prime to B prime, then I have some function, let's call it V, that goes from A to B, right? So that's a member of this set, a function from A to B. I want to define a function that goes, let's say W, that goes from A prime to B prime, right? How do I define this function? I have at my disposal this function, and I have F and G. Well, if somebody gives me A prime, then I can apply F to A prime, and it will give me an A, right? I have to precompose this with F. And then I can use V to go from A to B, and then I can post-compose it with G to get B prime, right? So W is equal G after V after F, right? And you see this is essential, that because I'm precomposing with F, F has to go from A prime to A, it has to go in the opposite direction. In other words, a profunctor, the first object is sort of the source, and the second object is like the target, right? So if I want to lift something like this, I have to precompose the source. Or you can think of it, if you think of functors again as containers, you know, this is sort of a container of B's that is keyed by A. So A is like the key. So if I want to lift it, I have to precompose the key. I have to like translate the key from the new value to the old value, then use this to find a value, and then post-compose to get the new value, right? So this is how this works. So profunctors are important because of this main example. If you want to generalize somehow the home functor, you know, this is, you get into profunctors. And of course, notice that in this case, both elements are from the same category, C, right? So I said in the most general cases, these are two different categories. From now on, I'll just make it the same category. So this is C op C to set, right? This is from C, this is from C, right? F is from C op G is from C. Okay? Another good intuition for profunctors, and this is related to the Curry-Howard isomorphism, is you can think of a profunctor as establishing some kind of relation between objects. Right? I mean, in a sense, having a morphism between two objects means that they are somehow related. Right? You can think of them. And it's like in a pre-order, having a morphism between two objects means one is less than the other, which is a relation, right? So it's a kind of trivial set. The home set is kind of trivial. It can either contain a single element, which means yes, it's less than, or be empty, which means no, it's not less than, right? But in general, you can have multiple morphisms between things. And you might think of a profunctor. A profunctor is a mapping that takes two objects and produces an element of a set, produces a set. So you might think of this, if the set is empty for a particular pair of objects, it means these objects are not related. Okay. If it's non-empty, it means these objects are related. But why do we need this whole set, right? Isn't it enough to have just one element that says yes or no, right? So you can think of this as a relation that comes with a proof. And why can you can have multiple proofs of this relation. So each element in the set here will correspond to a different proof that A is related to B. If the set for a given pair of AB, let me rename them on the fly. Okay, so if for a given pair of A and B, this set is empty, it means they are not related. If it's not empty, it means that we have several proofs, one or more proofs that they are related. Okay, so that's another intuition about how you can think of profunctors. Okay, so profunctors are functors. Okay, obviously. So since they are functors, we can have natural transformations between these functors, right? The natural transformation, well, it would sort of take a, take an element from C of C, right? So we have one profunctor. So profunctors are like called P, Q, and so on. I'll be calling them like. So we have profunctor P, and it maps A and B into P, A, B. Okay? So this is in set. Now suppose that we have another profunctor Q, right? And we will map the pair AB into QAB. The natural transformation between these two profunctors would be a family of, in this case, functions, right? Family of morphisms, but these are morphisms in sets, so they are functions. So this is like a family of functions that's indexed by AB. We take some other A prime, B prime, we'll get another morphism, another component of this natural transformation. Now what is, but the natural transformation has to satisfy naturality conditions, right? What would the naturality condition be? Well, a naturality condition would mean that we have to kind of draw a square here. So we not only need AB, but we also need some kind of A prime, B prime, another one. And this one is also mapped by P. It's mapped into P, A prime, B prime. And Q maps it into Q, A prime, B prime. Okay? And that there is a component of our natural transformation, A alpha A prime B prime, right? So this is the same picture but for a different point, right? Different component of natural transformation. But now, because these are functors, there is also a different path. Namely, we can go from PAB to PA prime B prime using factoriality, right? We have we have here a pair of morphisms, f and g, between these two, right? We can lift them, right? So if we lift, and I'll write it as p, f, g, right? And remember that f goes in the opposite direction. So p, f, g is the lifting of f, g, of this pair f, g, right? That goes from PAB to PA prime B prime. And the same we can do with Q. So we can have the lifting of F and G using Q. So this will be Q F G. And now we have a square. It goes like this, this, or like this, this, right? So that's our naturality square. And now you are probably curious, like, oh, okay, so what does it have to do with programming, right? I haven't explained. So in Haskell, we would write a profunctor as, like any other functor, you know, as a type constructor. So it takes types into a set, which is also a type, right? So it takes a pair of types into a type. So we would say class profunctor P where, okay? So P is now a type constructor that takes two types to create a type. Okay? Just like a functor takes one type and creates a new type, like a list of integers takes int and creates a list of int. Here it takes two types and creates a new type, right? So in order to get a type out of it, I have to apply it to two different types. Okay? And just like with functors, I had to specify how it lifts, which means defining fmap. Fmap lifts a single function. Here, I'm lifting a pair of functions. Okay? So this is called dymap. Takes two functions. One function goes from A prime to A, A prime to A. Okay. How do I fit it here so that everybody can see it? Another function that goes from B to B prime. Okay, that's my G function goes from B to B prime. And it produces a function that goes from PAB to PA prime B prime, right? So PAB to PA prime B prime. I can put it in parentheses, although it's not strictly necessary, right, because of kerning. But this is very analogous to a functor, right? In a functor, you just have one function and you lift it, and this is the functor acting on A, functor acting on A prime. Here we have a profunctor, so it acts on two types, and here two types, right? And I get a function, lifted function, okay? Let's take a break.